Well, hi everybody. I hope you guys are not tired. If you guys are, I think I'm going to keep this last talk a little bit light. But the goal here is more so to leave you with some questions and probably to combine together everything that you've learned throughout the conversation, throughout the talks, bring it all within like a single picture. So my first question before I go into the actual talk would be, and I know I'm supposed to introduce myself. I hate introducing myself. So I will introduce myself. Give me 2 minutes. I'll take time to introduce myself. But in the meantime, I'll ask you this question, which is how many people here are experimenting versus building with large language models? And my second question is, are you from the engineering side or are you from the business side? I know I should have asked these questions from Amir, but I want to make sure that people are still alive. If you guys reply, I know you're listening. If you don't, I know you've left me alone. But anyway,
Yeah, please put the answers in a chat as we go, and we'll take a look at them. Yeah.
While the answers come in, I'll do a brief intro of myself. So hi everyone, I'm Abby. I am a machine learning engineer. I've been doing consulting, basically deploying machine learning models, building and deploying machine learning models in production for quite some time, about 2 years, though I've technically been in the field since 2016. But a lot of us who started early in the field back in 2016, 2017, we were just doing a lot of Jupyter notebooks. And there was not a lot of, the sophistication wasn't quite there the way we have today. There weren't enough tools for the pipelines and all of that stuff. So the world feels very different now. Outside of that, I also am currently working on a startup where I'm building orchestration tools for agent-based models, basically AI agents, you could call them. One of the topics that a lot of people, I assume, would be interested in, we can talk about that later if you guys are interested. Outside of that, I'm also writing a book for O'Reilly on LLMOps, trying to talk about the fundamentals of why we need certain tooling, what are the limitations of those tooling and everything. Outside of that, I'm also doing one more consulting thing, which is basically I'm helping a VC fund with their investment thesis for large language models, LLMOps space, or you can still call it AI/generative space, because almost everybody's integrating AI in some way or the other. And so I usually go in due diligence meetings and just help out with the, should we invest and should we not invest, just giving my feedback. I don't know anything about finance. So that's all there is to know about me, which is my primary interests are in machine learning engineering and startups. So however I can integrate those two interests together, I am doing it in all the possible ways. So looking at the answers right now, there are a lot of people who are MLOps engineer, business side, plus experimenting, engineering. Okay, most of the people are experimenting right now. Okay, perfect. The reason I asked you guys this question is there are two ways we can look at the models. So the first way is, most of the times when you're experimenting with the models, you're looking at essentially like the proprietary models, the OpenAIs and the Claude and the Cohere and all of those APIs, versus when you're building your own model, then you have that question, or when you're building a product, you have that question of, should we still use the API-based model, so should we develop our own domain-specific large language model, something which Farhad. Okay, I'm very bad with names, but the person before me touched upon. So that's the main reason we're having this conversation, which is how do we decide when to build versus when to buy? What are the things that we need to think of when we're thinking between those two things? So basically, the first touch point, I think while you're in experimentation, you're not essentially thinking about, are we going to succeed or are we going to fail? Because um, essentially, experimentation does allow you to fail. Whereas eventually, if you're ending up building a product, one of the core focus is generating revenue, which is again one of the discussions the speaker before me did touch upon, which is like a lot of companies are interested in how do we make revenues out of these models, which is one of the things that was missing in the conventional machine learning world. It took us a very long time for, I think, a lot of data scientists to be able to realize that you have to figure out some way to be able to tie the business KPIs with the basically with the performance metrics. That could be accuracy, that could be the precision or recall, whatever your performance metrics were. Just having good enough accuracy wasn't enough to be able to explain in the business terms, to be able to make real business difference, which at the end of the day is either generating more revenue or cutting down the cost for something, whatever your product is the main factor as to whether we can scale that team or whether we can keep putting resources in that team, or whether it is something that, next financial thing hits and we have layoffs. So, it becomes important. So basically, the thing I wanted to say is a lot of machine learning projects in the past did fail for quite a few years, with only a few projects that actually made it in production. Well, there are 4 reasons, and this was a study that was done by Gartner, and they said, well, there are 4 reasons why a lot of these projects ended up failing. It's not basically that the model was failing, but it was more like the ops side or the people side of things that were failing. So for example, lack of business use case clarity, which is, do we really need to apply ML? Can we somehow tie those performance metrics together? The second is inadequate skills within the team for end-to-end deployments, neglecting organizational change, failure to experiment. So some of the obvious reasons that everybody knows, but I think the first reason, which is a lack of business use case clarity, is something which is one of the most pressing things now that, again, we start talking about, integrating large language models. Sure, they're fancy, but one of the reasons we see so many experimentations, so many demos, is because not a lot of people have figured out, which is there actual revenues that will be generated out of this, while there are some use cases that I've seen. So for example, podcast summarization tools, or copywriting tools, where I've seen, clear implementations and products. But outside of that, there are so many other use cases, like something Amir said, which is you can use a large language model anywhere you can use a language to communicate with the computers. So whether that's to be able to query anything, whether that's to be able to interact with the website, whether that's to do anything on the audio or speech side, you can use large language models. But the point is whether it is able to give you enough value to sustain the project in the long run. And the thing with that is basically, are we able to build reliable products in the long run? So what we believe is basically there are 3 pillars of success. These 3 pillars are basically generalizability, which is how well does your model adapt to the changes in the data. The second is basically, is your model evaluable? And the third is basically, is your model cost optimal? These are the 3 things which are commonly desired in any machine learning, especially like in any LLM deployment, but generally speaking in any machine learning product or application deployment, which is, it has to be generalizable. We can't keep building rule-based models. It has to be evaluable, because there has to be some sort of way to be able to assess the performance of the model, and it has to be cost optimal, and cost optimality would differ for different companies. And basically, we looked at a lot of use cases. One of the things we realized is at any point in time, you cannot achieve all the three things together, which is either you can have a model that is generalizable and evaluable, but then it wouldn't be cost optimal. Because to do any sort of evaluation is already hard to do. Now, bring in a large language model to be able to do evaluation on a large language model would require a lot of investment in the human cost of human evaluators doing it. Because yeah, there's no other way to be able to do it any other way. I mean, there are options, which is, like you can build a feedback model, but it's still expensive. So you can't bring down the cost if you're trying to optimize generalizability and evaluability at like the top notch. Second is basically if you're making it evaluable and cost optimal, then it's very hard to get generalization on the model. At least not the generalization that OpenAI is able to get. Because if you don't have enough, if you're trying to cut down on the cost, then that means cutting down on the training, which does mean that you can either build a specific model for a very particular domain, or the model wouldn't really perform as well if you end up not training the model enough. If you pour a lot of data into it, but still not train it enough, it's not going to have good performance, generally speaking. So basically, all three of them are sort of orthogonal, and this is something basically we call the GEC framework. For generalization, these are the 4 use cases. Commonly speaking, these are the 4 use cases, but obviously there will be more use cases. So as of now, if you've looked at several economists who are trying to figure out, where can large language models make a difference, as of now, it's basically very hard to be able to predict, which is how would the workforce be impacted. But speaking of right now, it's used for knowledge retrieval. It's used for recommender systems. I mean, I know a lot of people may not have seen implementation of recommender systems, but there have been quite a few papers, and the performance seems to be better. At least, I mean, I've seen a couple of papers with SOTA results. I've not really seen any implementations of recommender systems and for any aggregation website, you could say. So I've not seen large language models being deployed in production for recommender systems. But in terms of, is there promising enough performance for somebody to be able to deploy it? Yes, for sure. But once they've figured out the other things that we'll discuss throughout this conversation. The third is cross-lingual translation. This is something Cohere is focusing on, which is basically like if you have a company that has documents, let's say you're a European company that has documents in several languages, ideally, all of that information is isolated from staff that doesn't really speak that language or that is based in different continents. So to be able to bring that together is basically like one of the other use cases. And finally is the AI agents. So the question comes, which is, okay, sure, we want to build a model that's generalizable enough. How do we decide which provider or which foundational model would be a better choice? So, I mean, it's almost like a decision that you can make. I mean, right now, there are a lot of people who will simply say, oh, if the model has better context windows, it's going to be better. But I think there have to be a couple of things, which is you have to look at the number of parameters, you have to look at the size of the context window, you have to look at the training type, which is it encoder or decoder? Is it encoder decoder? You have to look at inference speed, cost, fine-tunability, as well as data security. So all of these factors considered in would provide a substantial answer. And before this, maybe one of the things that would be important to look for is if the model is available or not. So I've not included basically the compliance side of things, which is the EU security law that may end up limiting the availability of some models in certain regions. But given that the models are available, this is basically the list of things that you have to be looking for. And while the model quality would depend on the particular domain as well as the sophistication of application that you're building things on, which, for example, like it depends on the data which the model was trained on. So for example, OpenAI was trained on majorly unstructured data, so the performance is slightly better on unstructured data. However, the models that are trained on structured data, and this is one of those things where a lot of people say, oh, GPT has fantastic performance on almost everything, it is intelligent and whatnot. And the best answer to give them is basically this, which is, if you're assessing the task performance on structured data or unstructured data, if we are looking at entirely structured data, then the performance may not be as good, and it depends, which is how is the data structured, and how much of the data do we have available to us. Then what does the storage system of that data look like? So those are things to think of, and that would sort of decide which is how or which model do we end up choosing. So here's a quick checklist for model selection, which is thinking about whether the model is open source versus proprietary, which means basically, do you have the model parameters available to you or not? One of the most important things, especially when it comes to evaluation, is, do we have the model parameters or not? So that would be the first question to ask. The second thing is, what are the number of parameters? So obvious answer here is, if the model has higher number of parameters, chances are the performance is going to be better. So simple reason is, I think the logistics of GPT-2 versus GPT 3.5 versus GPT-4, where GPT-3 had about 175 billion parameters, or 175 million. I'm sort of missing out on those ones. I think it was 175 billion, whereas GPT-4 has about 220. And I was reading a paper almost today itself, and the paper basically said, other than the number of parameters, the only thing that is different between GPT-3 and GPT-4 in terms of the performance, basically the feedback loop, or how much. The only bottleneck is basically the feedback model that is being used, the number of feedback that is going back into the system. So technically, the model hasn't really improved other than just the parameters, or other than the RLHF, which we're seeing on the model. The third thing is basically, is the training data available? That would make vast amount of difference in deciding whether we should use that particular model or not. There are some open source models. So for example, the ones that are available by AI21 Labs, some are available by Luther. So if the data is available, of course, you can look into it, you can debug it, and you can obviously evaluate it much better than if the training data is not available. Inference latency, cost of inferencing, is the model fine-tunable? This is something I don't think most people do know, which is, not all of the models are fine-tunable. So that is another thing to think of. What is the cost of fine-tuning the model? Another difference, which is basically the cost of fine-tuning versus the cost of inferencing, is different, which is fine-tuning is, at this point in time, about twice, or depending on the model itself, from twice to 4 times as expensive as just inferencing. So is that the cost that we can actually maintain, or is that the cost that we can scale with inside the company? And the last question would be, what is the size of the context window? And this is something we'll go into in one of the future slides. So these are all the questions and in the series that you need to be asking before deciding whether we build or versus whether we buy a model. If you don't have an option, which is, let's say if it's a startup, it makes perfect sense to be able to buy and experiment quickly. But at a certain point in time, the biggest limitation is basically on the reliability side of things. And what I mean by that is there are currently not enough policies around long-term support of the models. in the absence of the LTS policies on how the model, when the model is going to be deprecated, and how much support would be available past that deprecation, does sort of answer that question of do we build versus do we buy, because any of the prompts that you've written around it or any fine-tuning that you've done on the model would require retraining. I mean, not all of the prompts go bad, but there has been a substantial prompt drift that has been seen on at least like the things that I've built. Transitioning from model 3 to model 3.5, a lot of prompts ended up being useless. And so a lot of work was actually wasted. GPT-4, yep. So basically there was a press release yesterday from OpenAI saying, the older models, I'm not entirely sure what do they mean by the older models, but the older models are going to be deprecated. So they've not really specified by the end of the year which of the older models, whether that will be 3.5 or whether that will be like the ones before 3 that will be deprecated. But as of now, that is something that we're talking about, which is the company can announce on a whim, and that depends. That the reason it's important is because there are different costs associated with different versions of the models. Doing inferencing on GPT 3.5 versus doing inferencing on GPT-4 would have different cost parameters as well, which does increase the cost of the product if you're thinking about it from like a revenue perspective. So in terms of build versus buy hypothesis, this is the sort of table that we put together to be able to decide whether we build or we buy. So the first question to ask is whether you have predictable workload. And this is the thing that we are talking about right now, which is a lot of people are experimenting here. So when you're experimenting, you don't really have a predictable workload. The moment you know how many inferences am I doing on a daily basis, or how many requests am I making to the API, at that point, it will make perfect sense to be able to build the model. Until you don't have that, the pay-as-you-go models tend to be cheaper, allowing you to reduce the upfront cost, but also allowing you that scalability in the long run. Maybe not in a very, very, very long run, but at least for like the immediate 1 or 2 years. Second is basically hardware cost. Do you already have the infrastructure? If not, then I mean the cost of basically being able to use the API is nominal, versus if the cost of building the system in-house is an upfront cost. And there's not just the cost of the GPUs, but also the maintenance cost of all of the hardware that you have in-house, which is the cooling and everything. Security. I think this is a little bit more obvious, which is basically building a model is obviously a little bit more secure as compared to whether you're buying the model, in which case your security does depend very heavily on the provider's infrastructure. If you've looked at the so Stanford did one of the assessments very recently on how does each model, each of the commonly available model compare against each other. That did show quite a few models that have massive loopholes in terms of their security, not OpenAI's, but the other ones. So I think it was done in response to the EU AI. I can drop a link if somebody's interested in looking at that comparison. It was done to make sure that to give all the models a marking between 0 and 46 on how does the model do in terms of compliance on the EU laws. And latency, building a model in-house would certainly have lower latency as compared to buying one, because you're pulling a lot of data from the cloud as compared to having something stored in-house. But here's the thing. Deploying any large language model is quite different from deploying a conventional model because of 2 reasons. The costs are twofold, or bifold, I should say, which is their infra-model related cost and their hidden cost. The infra-model related cost is something everybody knows about, which is, oh, sure, we need H100s to be able to build a model, and we do need this and that, and we need computers. But the hidden cost is something which is often ignored and not yet considered, and becomes one of the most important things to think of, especially when you decide to build your own model, or even if you end up buying a model from an API, then thinking about, what are the costs that are going to sneak up on me eventually as I use these models in production. So basically, the first cost is the cost of prompt or prompt engineering. So one of the most common questions that I see from a lot of people is, do we prompt engineer versus do we fine tune? And I thought that was important to address, because prompting versus fine tuning would have different costs as well. So I think generally speaking, if we're trying to do domain adaptation, then basically prompt engineering works better for embedding-based search versus fine-tuning, which does work better when we're doing categorization and filtering, where there's no sort of category that compares the generalization. For basically, as of now, I would say, there's no conclusive work in the field that says, whether prompt engineering is better or whether fine-tuning is better. It's definitely a question that you need to think of. Most of the people, I think most of you guys, would probably be doing some level of fine-tuning. And only once you've fine-tuned enough and you realize that this is just the amount of performance that we'll be able to get with prompting, that people start thinking about fine-tuning. But in my conversations with a lot of folks at Microsoft, OpenAI, as well as some of the leading banks, what they're doing is they're trying to fine-tune the models instead of trying to prompt engineer the models, purely because of reliability reasons. But again, because of the kind of data that they do have as well. But this is more like a good categorization if you're thinking about which technique to use. And again, it would also depend on the size of the context window of the model itself, and how the cost would be impacted based on the context window. So coming to the other question of the cost involved with longer versus shorter context window. Again, one of the things that isn't talked about, if you go to Reddit, one of the things people say is, oh, the longer context window is always better. So I wanted to give you guys like a comparison of in which cases a longer context window better, in which cases a shorter context windows better, and what would be the cost associated with each. So basically, the larger context windows are generally better because they have more in-context information, and the model can handle longer inputs. So for example, when we're querying for something like code, which is something I think a lot of us are using ChatGPT for, or any sort of models for, then ideally having the larger context window is slightly a bit more helpful. When we're giving in structured data into the model, having a larger context window is certainly better because it decreases the chances of hallucination. Because again, all of the input is contained within a model and is able to chunk down the information into larger windows itself. And while it does open up some opportunities for accomplishing tasks that were harder previously, but there are advantages to shorter context windows as well. So for example, one of the biggest advantages is does fine-tuning need very robust infrastructure? Not essentially. I think fine-tuning doesn't really require any intensive infrastructure. The only thing is it does require intensive understanding of the machine learning algorithms that you're using compared to fine-tuning. And I will talk a little bit more about it towards the end. I'll show you like the system architecture what does fine-tuning versus what does prompting look like on an architecture level. But in terms of your answer itself, which is, it depends on which model are you fine-tuning. So OpenAI has its own function that allows you to be able to fine-tune quickly, but some other models which are not fine-tunable, if you're trying to fine-tune those models, then it becomes a little bit harder. So does it require infra? Not essentially. It would entirely depend on which model I'll be looking at. But more than infra, it's basically like the team itself, where or the ML expertise within the team itself that does define which one should we go with. On the shorter context windows, basically they're easy to write, which makes them a little bit more interpretable, and especially if given the fact that you're doing so. Basically, given the fact that you're still learning, and there is a lack of interpretability on how the model is going to react. So the more we interact with the model, the more we learn how the model is going to perform or what kind of answers is it going to give. In those cases, it's much better to be able to catch a problem early and to be able to change your prompt quickly. Now that becomes a problem with the larger context windows because you've already spent tons of money. The models with larger context windows tend to be obviously 4 times more expensive than a model with a shorter context window. You know, like there's that quadratic comparison between the models itself. So once you've used the tokens, once you've made a certain call, you've ended up spending money. So, and in that regard, the shorter context windows tends to be better. Overall latency is low for the obvious reasons, because it's compiling information from different contexts as well. We're using chain of thought, but the chain of thought process becomes easy, and it allows us to be able to experiment more quickly. So if you're using a large language model purely for experimentation itself, if it's not being used for coding, or even if it's being used for coding, but you haven't interacted enough with the model yet, then a shorter context window is likely like a cost-optimal solution as compared to a longer context window. And you can also leverage parallel context window. This is something which is still ongoing work in the field that allows you to be able to increase the performance bifold without fine-tuning or without using an expensive model with a bigger context window. But it's still work in the process. I've not seen tons of implementations of it. Still very few research papers. Okay, next slide. Okay, these are basically the obvious cost. But now come the hidden cost. The hidden cost is basically, the first hidden cost is the prompt drift, which is there's very little reproducibility between the prompts as you change the model versions itself. And it's not just that, but anytime you're switching or shifting between different vendors as well, you end up paying a lot in terms of compliance, because you've made sure, like, let's say we've used one particular model. The moment we change that to a separate model, then again, we sort of train the model once again with the new vendor. So there's a lock-in that happens based on whichever model that you end up going with, which is whether we end up going with OpenAI or whether we end up going with Claude in the long run. Picking one does have that one limitation, which is the lock-in, plus you have to rerun and build your entire prompting infrastructure. As of now, there's no translation happening between different models. If you end up realizing that a certain model is not giving you good performance, transitioning to another technically is easier, which is, oh, you're just switching up your API key and defining the model differently, which is switching up the names. But in terms of like the entire validation and evaluation infrastructure and, you know, the prompts written on top of it, that is the work that requires extra cost once again. The second is basically with the traditional models, what we did is we hired annotators to be able to annotate data sets. Now, what happens with large language models is you need domain knowledge to be able to write good prompts. Now, that creates a dependency on the prompt engineer. In case that person chooses to leave, it becomes very expensive cost for the company. Also, there is no way to sort of automate the validation of prompts. So prompting, and essentially, whether, initially, while it may look like, oh, prompting is cheaper than fine tuning, so we should definitely go with prompting because it will save up cost. But eventually, if you go with prompting, this cost will eventually catch up. And I mean, it's hard to say which is going to be cheaper in the long run, but that's the reason we called it, when I was working on it, we called it the costly dilemma, because it is a dilemma. Which one do you end up picking? Okay, I'm very bad at moving my slides, apparently. One of the ways to be able to save money on basically querying is to be able to do query caching, which allows you to be able to reduce the cost. So basically, if certain queries are being made over and over again, so for example, for question answering, you can save them onto your S3 database. That allows you to reduce the cost. You can also concatenate different queries as well, which to allow you at least like a baseline answer in case you don't want to, again, inference the model once again, or basically pay for the API cost once again. If some things can be answered very quickly based on the queries that you have caching, then it makes perfect sense. So, it is able to save you cost in terms of in these four things, which is how many repeated queries do you have? What is the frequency of those? What is the performance of the underlying model? What is the cache hit ratio? What is the overall architecture of the LLM inferencing system? So this defines whether you choose query caching. So again, it's one of those things which isn't an obvious solution. A lot of people have painted query caching as like, oh, this is the overall solution. No, it's not. It does depend. It will help in some cases, won't help in other cases. Oh man, I'm seriously unlucky with this. So in terms of summarizing, in terms of like what are the costs associated with large language model applications, there are some upfront costs, there are some hidden costs. The upfront cost is the cost of the context window, the cost of prompt versus fine-tuning, the data infrastructure scalability. The hidden cost is basically the hidden cost of reliability. You cannot give out a poem in case OpenAI's model stops working. You can't say, oh, sorry, we cannot really give you answers on our website because the model that we are using is getting more load than usual, and they've given us a poem, so here's your poem. The people cost, which again, this is more so on the prompt side that we discussed, which is creating indirect dependency on one person, the compliance hardware, model drift, prompt drift. So these are the hidden costs. These are the upfront costs to think about whenever you're building production level applications. The final thing, or the final section of this talk, is evaluation. So evaluation is one of those things which is super important to be able to assess what the performance of a model is going to look like. Now, for the proprietary models, which is basically the OpenAI, Cohere, or Anthropic models, they are obviously trained on massive amounts of data, but that reduces their interpretability, as well as it reduces their reproducibility as well. Plus, the models are now available to you, and the models are becoming, a lot of companies are moving to closed version of their models. While, I mean, there are certain predictions that, will have a booming open source infrastructure in the next 6 months to come. Maybe it will happen in the next 2 years, but until then, it's picking one of the proprietary models does put you in that dilemma, which is, it's near impossible task to be able to fully evaluate those models. So how do we think about performance if you cannot evaluate? Well, we think about things like accuracy, we think about inference speed, and we think about latency. While that means we also would have to put on guardrails, but I'll leave that topic for like a different conversation entirely. How do we create stable experimental setups? I think this is one of the more important things to think of, because I think the performance is a little bit obvious, which is, of course, everybody's thinking about inference speed, latency, and accuracy. But how do we make sure that, the evaluation that we are doing is consistent. We're not adding any uncertainty that is affecting the performance. So there are 3 ways we can think about that. One is, how do we sample our data in test versus evals, making sure that it stays consistent. Logging the prompts and inference is one of the common solutions. Not the common solutions, but one of the solutions I've seen with some companies is using a feature store to be able to log the prompts. It's not that acceptable, which is it's not that popular yet, but some people are using feature stores for this particular thing. The next is basically checkpointing the models throughout the process. So basically, you can do early stopping, and you can also know, at what place basically the performance started to decline. So, it will be a little bit easier to look into the data or to look into that particular batch and to be able to remove certain data sets, because the performance of a large language model does very much depend on the quality of the data, or any deep learning model does depend very heavily on the quality of the data itself. So what does a good benchmarking system, or what should a good benchmarking system look like? It needs to have scalability. It needs to have incrementality, which is the model should be able to evaluate a new model using a relatively small number of trials, which is it's learning as we're continuing to use it more, and is able to have a unique order, which is basically, there should be a clear classification between which model is better, which is, this is number 1, this is number 2, this is number 3. So there's no draw situation happening. The generalized benchmarks, as of now, what you would most likely see is there are 2 kinds of benchmarks that are available. The first ones, okay, maybe I should say more than 2 kinds. The first ones are the proprietary benchmarks, which is OpenAI evals. Then there's also Aviary, there's Neo guardrails. This is by NVIDIA, this is by Anyscale. They've released it. These are obviously open source. But and evals hardness, I think this one is by Luther. But one of the core limitations of any evaluation benchmarks that you look at, they are too generalized to be able to give reasonable performance, which is the benchmark on a question answering system might work very well. It may say, okay, you performed very well on question answering, but does it work well on, let's say, a climate change problem, or does it work well on any other use case? That needs for you to create your own evaluation as well, and it doesn't really have that domain specificity. None of these evaluation benchmarks do have that domain specificity. The only problem with using OpenAI evals, and this was covered in one of the papers by Percy Liang, which is anytime you're exposing your data, even as basically to be able to do evaluation with OpenAI evals, you're exposing your entire data to OpenAI. So basically, anytime they're retraining the model, that data will go into the system as well. The other thing is basically there are some leaderboards that are available, but again, very much the same way, which is I think the leaderboards are available by AI21 Labs. Some are by, if you've heard of Allen Institute, they've put out some leaderboards for question answering, which most of the people are using the question answering leaderboards. But again, if you're not doing something which is close to question answering, which is, let's say, if you're doing recommendation systems, that evaluation benchmark may not be very helpful. The new option that is out there, which is some people have started looking into ELO-based systems, which is basically like a scoring system, the way we do it in chess, which is very game theoretical way of comparing models in a pairwise group. So this is one of the examples. They have like a collab available, but again, and I've not seen ELO-based systems being applied in any particular use case yet. This work is purely academic, I would say, which is they've put collabs and all of that, but again, I think we'll probably see ELO-based system evaluations in the future as well, to be able to compare, how the models compare against each other. So this blog is basically like, how does OpenAI compare against Claude and all of those ones. So they've picked out 8 of the most popular models and compared those on their own benchmarks, and they've proven that the ELO-based benchmarks tend to be slightly better than the other, like the common OpenAI MLs benchmarks. So basically, this is my talk. Though I'll take you through one more thing, which is not in this document. So when it comes to the system architecture, as of now, you can't call the model from the front end or the back end, but as of now, me and a couple of my friends, we wanted to break down the systems, because what mostly everybody is seeing is, oh yes, this is the API, we give the API, or we use a workbench solution, for example, AWS or G-Cloud or whichever workbench solution or any managed service that is out there. But what's happening behind the hood is something we wanted to be able to visualize. So this is the visualization that we've put together, which is either you're basically calling the model from the front end, which means you have the user interface components. These are the components. And this is probably not the thing machine learning engineers need to be thinking of, but this is more like, I think, for software engineers and people who are thinking about software reliability engineering, to make sure that we know how things do impact each other within the system itself, or where do the failure points happen, and how do we catch those failure points quickly, or where are the requests being made from, and how do we control those requests, or how to be able to optimize those requests. So basically, if you're calling the model from the front end, you have the LLM integration directly at this point, which is here. However, you also have the option of being able to call the model from the backend, in which case we do the integration with backend APIs. So we have the user interface components, we have the event bus, then we have the network layer, which does load balancing. Then we have the backend application layer. This is the part I think most of the people would recognize, because this is standard system design. So on the backend application layer, we broke it down into one are the user personalization based services, which is basically user modeling, data processing, manipulation. This is the conventional ML work that we're doing on analytics. You also have inference server, memory, cache. So this allows you to think about like the entire system if you're planning to build your own model on that level, which is how many layers are there and which layers are connected to each other and how. So in terms of the infrastructure layer, we have the web and cache server. We have then we have TPMS components where we can do sharding or we can do federation. We have the cache cluster. This is also calling the hardware resources. Hardware resources would include the server machine, CPU, memory, storage, load balancers. Now, this is basically the LLM development and deployment. And our backend application layer is calling this component. We're basically pulling the data. We're storing it in vector stores after downloading the data and repartitioning it. We're doing pre-processing, then we're doing some sort of tokenization on it. Then we're doing some sort of sharding, which would require us to be able to access the GPUs. Then you're giving it to the model architecture, which is your model, whether that's something that you've built or whether that you're using GPT-3 or GPT 3.5. Again, it depends. This is only when you're calling it from the backend. You have versionized tokenizers. This is basically what we call the checkpointing. So once you give it to the model, then you do fine tuning on it. You're also establishing models and checkpoints during the training process. This is where from the backend itself, we're doing prompt engineering while training the model. Once the model is trained, we're saving these different checkpoints. And obviously, a lot of these things keep going back and forth, and we're doing model evaluation. Once you've done model evaluation, then your inference does go back into the backend application. Once that goes back into the backend application, some of the things would be stored in the cache. Some of the things would move to the network layer where we think about how to be able to load balance so that everybody's able to get the inferences right and the event bus and then back to the user interface. So this is where the entire infrastructure look like. One of the reasons I wanted to show you this was recently A16Z put together this emerging LLM stack. This is the way that they've sort of defined what would the LLM app stack would look like. It's hard to say it's going to look like that. I kind of not seen any other LLM stacks, but that's basically our implementation of an LLM stack. Again, a lot of things are not really defined, but I think some things are very well defined here in terms of the playground. It depends whether you're doing few shot, but they've listed a lot of companies that they've funded. So I think that's probably my entire talk here, which is, I hope I was able to bring some things together, provide some sort of perspective on a couple of things. And well, I'll open it to questions now.